There's a goal for you. So here's the quandary, right? Let's suppose you've got some object going in a circle. Well, that's a pretty good circle. That's a good circle. Okay, so I know it's exciting. Okay. Oh yeah, I can do it many times. Just hold on. It's one of the only exciting things in this class. So we got. Okay. So in this circle has a radius r. It's got a velocity as we go around that circle of v. Okay. And this is known, by the way, since that velocity is tangent to the circle, then therefore it is a tangential velocity. Okay. Please don't say tangential velocity in my class. Okay. I've got kids that say that, but yeah, it's all over once you say that. Why, Okay. But anyway, there it is. This is our tangential velocity, and so the notion is, if we could do this, and this is the quandary, right? Is that if I had a mass on the end of a string, and I twirled it, okay, and I stuck a real sword up there. Of course, the real sword, there's going to be some amount of, like, before it cuts, it's going to wrap around the sword, right? But if it's a lightsaber, okay, and I think this is a real lightsaber, okay, if I turn it on, if I just simply press that button that turns it on, and the lightsaber goes up there and intersects the plane that thing is moving in, the question is when it goes shoo, and like cuts it off, which apparently can cut it off with no resistance at all, right? Okay. Which way is it going to go? Is it going to go straight back toward those cabinets? Is it going to go sort of off at an angle away? Because I certainly, when I spin this, I certainly feel a force in there. There's a tension. It seems to me that when it's right there, I'm pulling it this way at that instant, is my impression. Okay? So is it going to fly that way? Because I'm pulling it this way and it's moving this way. So if I let go of it, does it fly that way? Is it going to fly that way? Is it going to fly, right? So the question is, does it go C? Does it curve way out like this, right? If I let go, is this thing going to curve this way? Is it going to continue sort of going in a circle, but maybe not quite as here? Maybe not quite as like that, and just kind of, yeah?
Yeah, that's what's going to happen.
Do we have any?
I bet on the first one.
This guy here, it's going to shoot out to the outside. How many say it's going to shoot to the outside? How many say it's going to go straight off at a tangent? Clear majority for that so far. How many say it's going to kind of spiral its way out? There we go. Yeah. Okay, now let me rain on your parade if let's just think about this, right? Because the question would be, here would be my question, right? If you believe Newton's first law, nobody's really questioning that at this point in science, right? Newton's first law states that objects will travel in a straight line at a constant speed, yes? Yes. Okay, so certainly it'll do that unless there's an outside force acting on it. Now presumably this roll of tape is going in a circle because why? It's not going in a straight line. It is going at a constant speed, more or less, right? Yeah, I'm pulling this thing, yes, aren't I? I believe I'm pulling it toward the middle, yeah? So I'm pulling this thing toward the middle to make it go in a circle, right? So if I stop exerting a force on it, let's suppose I'm in outer space and there's not gravity to confuse things, right? If I stop exerting a force toward the middle, what's it going to do?
It's going to go, it'll keep trying to go in the same direction it's going, plus the straight line momentum.
It's going to remember somehow that it was going in a circle and try to go in a circle. What's going to make it go in a circle? But the string's gone. So if the string is no longer exerting a force on it, what's it going to do? It's going to go in a straight line, is what I'm heading toward, right? Yes?
Yeah.
So for sure, if you look at the drawing up here, A and C are curved, and there's no way it's going to curve like that, right? It's definitely going to go in a straight line. Then the question is, what does it do, right? Which direction is it going? And I would argue that it is moving tangentially at any instant, right? So therefore, it's going to fly off at a tangent. We'll just try it here. We'll see if I got enough coordination, right? If I release it when it's there, you might want to like protect yourself a little bit, because maybe if I release it, in the wrong place, it might, or if, right? So, okay, you guys ready? Sort of cover your face a little bit. Okay, this is good. This is good. Okay, I'm going to release it when it's right there. Release, 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 release. Whoa, baby! Here we go. Okay, so you guys were safe. Okay, it flies off to the side, and we very rarely injure people. You know. Okay, so yeah, sure. If I release it right there, it's actually going to go there. Now, has anybody ever made a sling, as in like David slew Goliath type thing?
Yeah. No.
Have you ever built one of those? I grew up in Iowa, and there's very little to do in Iowa, and so we made slings. We made slings. A friend of mine made a sling, and it's very simple. You just need some cord. This is about the right length for it. You can try shorter, longer. Okay, there's benefits of both. And then all you need is 2 strings like this. One of them, you put a loop in it and loop that over your finger. You never let go of that one. And then the other one, you are going to release it. That's the release, right? And then what you do is you just get like a little leather pouch. You just get a piece of leather, shape it like this, drill a hole there, wrap it around a stone, yeah? And spin it, and if you can throw a rock fast, with a sling you can throw it like nuclear fast. I mean, you can make little quartz rocks that just bounce. When you throw them, they just bounce off the Indian Creek Bridge. You can make those things shatter when they hit the Indian Creek Bridge above it. Any rock will just shatter into fine powder. You can throw it so hard. They really should not be legal. Right, and everybody knows when you're slinging, right? You go woo 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 woo, right? When you want to hit there, you're releasing right here. So there is a little bit of a coordination thing. But boy, if you just practice, you can get good with a sling. Slings are just amazing things, right? And that's because the reason they're faster than your pitching arm is that there's a longer radius, right? Your pitching arm the ball only goes as fast as you can snap your fingers at the end, right? But a sling, you can get that going a bajillion miles an hour and then release it and it flies off, right? Okay. So the answer, if you're looking for the answer, is that it does fly off tangentially, right? But where we're headed right now is that there's 2 kinds of accelerations. I would say that an object that's going in a circle like this, okay, is not going at a constant velocity. Yeah? This is not a constant velocity. In order for it to be a constant velocity, it has to be a straight line, right? So it's not that we're changing the speed part of the velocity. What are we changing? If we
The XY speed.
The XY speed. What are we changing? What is velocity? Velocity is speed and direction. We're not changing the speed, so therefore we are changing the direction. Yeah. Okay. So with this kind of acceleration, we're actually just changing the direction, right? So there's 2 accelerations that we've had. The first kind is linear acceleration, right? And linear acceleration was the object's moving this way. That's its velocity, right? And then the force is either in the direction of the velocity, in which case it speeds up, right? And then it could also be opposite the direction of the velocity, in which case it slows down. Yeah? Right? So that's all we've done so far, and that was challenging enough. Now what we're going to do is we're going to look at accelerations called centripetal accelerations. Okay? With centripetal accelerations, the velocity is this way, okay, and then the force is just off to the side. Right? So we have a force this way, and there's no great mystery here. If the force is to the right, this thing's going to curve to the right. If the force is to the left, it's going to curve to the left. Okay? Now, this is sort of so here this thing changes the speed but not the direction. This one changes the direction but not the speed. Yes? Okay? So this is how the Earth has been going around the sun, presumably since its creation 4.5 billion years ago, right? And it's not going any faster, it's not going any slower, and that's because the force of gravity has always been a centripetal force. It's always been at right angles to the velocity. Right? And it makes sense, right, that a force at right angles to the velocity doesn't speed it up, doesn't slow it down, just steers it. Yeah? That's kind of cool, right? Okay. Now, you can read the textbook. Douglas Giancoli, bless his heart, tries to derive the formula for centripetal acceleration. And he does this whole thing about, basically it's calculus, and that's why you can't understand it, because he's trying to do it with algebra. Okay? So I'm just going to say, here's the formula. Okay? The acceleration formula, centripetal acceleration formula is, and I'll just erase this because we already know that. Okay? Yes, it is, right? It's just v squared over r, right? Now, this should make sense because if you think about it, think about the g-force that you feel when you go around a corner.